Thank you so much. Um, Thank you for tuning in at this possibly very inconvenient hour wherever you are. Um, Please interrupt with questions or comments during the talk so that I don't feel I don't feel that I'm talking to myself. Um, yeah, so you can just unmute yourself and interrupt at any point. This uh, presentation is based basically on this work that appeared very recently with Kentaro Omori, Konstantinos Rompedakis, and Sahan Saif Nashri. Konstantinos is now at UCLA, and Kentaro and Sahan are in Stony Brook. Also, there is a huge amount of literature on the subject that I will probably not refer to very systematically during the talk. So I just wanted to flesh out some papers that are very important for what I'm going to say. I'll try to be more or less self-contained and explain what explain the concepts that I'm using. But I will not, of course, there will be some things that I will not prove or will not explain completely. I am happy to talk about them in the half-an-hour discussion session afterwards. But in any case, these are some papers that are kind of crucial for many things I'm going to say. But as I said, I'll try to keep them in the background so that you can still follow the talk, even if you do not know the content of some of these papers. Okay, so let me start with a very elementary introduction that will be definitely boring for all of you. But just to set the stage and the terminology that I'm going to be using, of course, we know that symmetries are very important. And the basic statement is the Noether theorem, which relates the existence of continuous transformations or continuous symmetries with conserved currents. And associated to this conserved current, there is a corresponding conserved charge. And the claim to fame of this conserved charge is that it's independent of the slice over which you integrate J naught. So you can actually integrate over any space like slice, and the dependence on this slice is drops out because of the conservation. Now in quantum mechanics, these charges are promoted to unitary operators on the Hilbert space. So unitary operators U that act on the Hilbert space. And if the symmetry is continuous and we have Noether's theorem, we can write a very explicit expression for these unitaries, which depend on some transformation parameter alpha in this way. And sigma is some space like slice, which, as I said, actually doesn't make a big difference because the unitary doesn't depend on it for small deformations. Now, this cannot be done as explicitly for discrete symmetries, but for discrete symmetries, it is still true that there is a unitary that acts on the Hilbert space, though we cannot write a very explicit expression in terms of the fundamental fields usually, but it still exists. And now we know how to act with symmetries to get word identities. So if you have an operator, the action, so this line is like a codimension one space like slice. And from now on, I'll just use Euclidean signature. And this is just a codimension one surface. And it acts on local operators in some way. So operators are in some faithful representation of the symmetries. And you can also compose the symmetries. So you can take two codimension one slice, codimension one surfaces, compose them, and the order potentially matters, right? If you do first G and then G prime, or if you do G first and then G, if they don't commute, the order is important. In any way, you can fuse them to GG prime. And actually there is a typo here. It's supposed to be G prime G because you act with G first and then G prime. So I'm sorry for that typo. And of course, if you open books on QFT, you're told you learn how to do many things with symmetries. We can gauge symmetries. We can have anomalies. They can be spontaneously broken, explicitly broken. and so on. Now, a lot of recent work that has really been quite popular, I should say, both in the condensed matter community and in the high energy physics community, was to explore generalizations of the notion of symmetry. So you might not think that any generalizations exist, but actually there are very important and interesting generalizations. And I'll talk mostly about one such generalization, but I'll mention some others, and they will be somewhat important for some things I say. So mainly two types of extensions of the notion of symmetry were discussed in the recent literature. Before I talk about them, maybe I'll stop here to ask if there are any questions about the introduction, about the existence of unitary operators that obey the group law. And are there any comments or questions about it? Okay, so I'll continue. So there are two types of generalizations that were discussed in the literature. One is when your unitary operators are not associated to a codimension 1 surface. Rather, they're associated to a codimension 2 surface. So they depend on a d-2 dimensional. You are integrating over a d-2 dimensional space, rather a d-1 dimensional space. Such things are called higher symmetries. And this particular case corresponds to what's called a one-form symmetry. And you've probably seen many papers about higher symmetries and one-form symmetries in various quantum field theories in various dimensions. And this is what it is about. It's about unitary operators that depend on a lower dimensional surface, topologically. In this talk, I'll be interested in something else, which is the situation which is a little bit more surprising. And that's the existence of d-1 topological surfaces. So something like an ordinary symmetry. It's not a higher symmetry, but they're non-invertible. And the existence of such things is very confusing because it's really a very violent violation of what we think about as symmetries. So these are some conservation laws that are associated to codimension 1 surfaces, and they obey similar rules that we'll study in this talk, but they're not associated to any symmetry, and they're not invertible. The non-invertibility means that when you realize them as operators on the Hilbert space, they're non-unitary. So they violate the whole idea of Wigner's classification of symmetries as being unitary or anti-unitary, because these are some conserved quantities, so you can call them symmetries, that are not invertible or non-unitary on the Hilbert space. And of course, for ordinary symmetries, they're always invertible since they correspond to a group. And in a group, there is always an inverse element. Okay, so here, the idea is that there are some symmetries, or, well, I'll use the name non-symmetries because they're not associated to ordinary symmetries and they cannot be derived from Nether's procedure since they're non-invertible or realized non-unitarily on the Hilbert space. So I'll sometimes use the name non-symmetry. I'll mention that in the condensed matter community, these things are called defect symmetries. And in the mathematics community, they're called category symmetries. Okay, these are names that appear in the literature interchangeably. They more or less talk about the same things, which are symmetries that are not realized unitarily on the Hilbert space. Okay, now to convince you that such things exist, I'll go through the simplest possible example, which is a pedagogical example. Then I will talk about the gauge theory in 2 dimensions that surprisingly admits many such symmetries. And the existence of these symmetries in this gauge theory explains many facts about this gauge theory and allows to do new computations. That's the plan of this talk. So first I'll go through some pedagogical examples. Are there any questions about the definition of, about what I'm going to talk about, which is this concept mostly? I should also say that I'll concentrate on 2-dimensional theories, and I'm happy to discuss what we know about higher dimensional cases later, but most of the talk will be about d equals 2. Okay, any questions about that? Or I'll start the pedagogical example. Okay, so the simplest non-trivial example that exists for these non-symmetries or non-invertible operators, non-unitary operators, is this. So let me go one by one, unpacking what is written here. So one object is a unitary. So U is an ordinary unitary, which is a Z2 symmetry. So this is a system with an ordinary Z2. There is nothing surprising or exotic about this U2. It's a system that obeys an ordinary unitary Z2 symmetry. And you can see that it's invertible. Since you act with this unitary twice, you get one. And then there is a more interesting element, which is denoted here by curly n. And it's commutative. That's one thing that's non-generic. That's why this is the simplest example. But n with U, they are commutative, and they give rise to n. But the most important equation is what happens when you take n with itself. Then you get 1 plus U. And this is the algebra, okay? Well, I say the algebra, it should be called mathematically a fusion category, but I'll just say the algebra, abusing the terminology a little bit. Now, it's actually a fun exercise to make sure that this is self-consistent. So you can take these rules, multiply by another n here, or multiply by U, use commutativity, and see if you can get a contradiction. And it's a fun exercise to see that this is actually completely consistent. It's clearly not a group, and clearly n is not invertible, because there is nothing you can multiply n by to get 1. So this is the simplest example. And now I'll talk about some ways to realize it on interesting physical systems. And we will actually see later a gauge theory, an SU2 gauge theory, which has exactly this symmetry. So this could be the full symmetry group. Sorry, this could be the symmetry group of a full-fledged quantum field theory, namely a whole RG flow from the UV to the infrared could obey this symmetry. It could end up in a gapless model, or it could end up in a gapped model. Namely, it could be gapped or gapless. There are systems with the symmetries that are gapless. There are systems with the symmetry which are gapped. We'll see some examples of both. In particular, the minimal model, which is the Ising model in 2 dimensions, has this big symmetry. This was shown by Verlinde many years ago. This is when he constructed what the so-called Verlinde lines. So Verlinde showed that this thing can act on the gapless Ising model. And here I'll summarize how it works. So if you look at Verlinde's paper, he basically showed that this non-invertible line n annihilates sigma. And just from this, you know that this is non-unitary. Because if you think about sigma as a state on S1 via the state operator correspondence, there is a symmetry that annihilates it, that annihilates the state that corresponds to sigma. So clearly this cannot be an invertible symmetry, but it's still a symmetry. Then if you fuse 2 such lines, you get 1 plus U. And also one additional fact is that if you try to stretch sigma through this non-invertible line, you get the line U, which is connected to the disorder operator mu. So this line U can end on the disorder operator, and it's connected through this junction. And that's this diagram is just correct. This is the same as that and the same as that. So this is how this line acts on a gapless model, the minimalizing model. And let me just say that something that Verlinde did not study was the question of whether this is just a symmetry of the Ising model, or it could be an interesting symmetry of a whole RG flow that leads to the Ising model maybe. And the answer is actually yes, that there is a whole RG flow that can end at the Ising model and be completely consistent with this large symmetry. So you can think about it from the Ising model as deforming by TT bar. The TT bar operator is invariant under N, and it's invariant under U, so it preserves this funny algebra, and you can flow up to the UV. And this flow basically ends at the tri-critical Ising model. So the whole flow is consistent with the symmetry. But notice a fun fact that you cannot flow out of the Ising model. So we usually when we talk about the Ising model, we have a deformation that preserves the Z2 symmetry, which is the energy operator. The energy operator preserves U because it's Z2 invariant, but actually doesn't preserve N. I did not write how N acts on the energy operator, but it flips its sign. So any system that flows to a gapless that flows to the Ising model cannot actually flow out of the Ising model if it obeys the symmetries, because no relevant deformation of the Ising model is invariant under the symmetries. Okay, so this is how it works on the Ising model. What about if the model is gapped? That's a more recent question that will be very key for what I'm going to tell you of whether these symmetries can act on gapped states. So first I have to tell you a little bit about what are gapped states in quantum field theory in two dimensions, and then I'll try to tell you how these symmetries can act on them. So as many of you know, it's very hard to classify gap theories in higher dimensions. Like in 3 dimensions, this could be, gap theories could be complicated. There could be Chern-Simons terms in the infrared, and the classification is very difficult. But in 2 dimensions, namely 1 + 1 dimensions, there is only one possible compact manifold without boundary, which is space-like, and it's the circle. So it's only the only possible space-like manifold that's compact without boundary. And so a gapped 2-dimensional theory is pretty easy to classify. The technical term is called the Frobenius algebra, but you don't need to know anything about it for this talk. I'll just tell you some basic facts. So all there is to a gapped quantum field theory in 2 dimensions at the very long distance limit is a bunch of states which are exactly degenerate on S1. So you take the long distance limit, you take a huge S1, you get the n degenerate states, you call it a topological field theory, and that's your infrared limit. And that's all there is to it. Actually, a very important subtle point is that in the full theory, of course, these are not exactly degenerate. Typically, if you have states on the circle in finite volume, there are small, exponentially small splittings. So there are exponentially small splittings in the volume of S1. But in the infrared limit, these are very small contributions. They're exponentially small. You drop them out, and you treat the states as being exactly degenerate. So a gapped 2-dimensional theory is basically just a bunch of states which are exactly degenerate on S1. And I'll call these states VI. So what I have to tell you is how to act on this VI with this funny algebra of symmetries. If this were ordinary symmetries, everybody knows the answer. We just have to find representations, linear representations of the symmetry, because in compact space you cannot have symmetry breaking. The representations have to be linear, and the states must fall into some big reducible representation of the symmetry group. The question is, what is the analog for such a thing which is not a group? So how do we act on these states on S1 with this object? Are there any questions? I'll just wait for 10 seconds if there are any questions about the setup. Okay. So here comes the first non-trivial claim. This is a difficult claim that I'm happy to explain now or later. It doesn't matter. But the most important claim is essentially the generalization of the notion of representation. So these states in the infrared are constrained, obviously, by this algebra of non-symmetries. But since there is no notion of representation, being that some of these operators are non-invertible, you have to come up with something else. And the generalization is called NIMREP. What is an NIMREP? It's a matrix with non-negative integer entries. So all the entries of the matrix are non-negative integer numbers. They could be 0, but they cannot be negative, and they have to be integers. So the basic deep claim is that this algebra of non-symmetries has to act on these states VI via some such matrices, which are represented by integer numbers, which are non-negative. This is a very basis-dependent statement. Unlike ordinary representations of groups that you're familiar with, when we say that the vacuum forms some representations, linear representations of some symmetry group, this is a statement that's basis independent. Here, the existence of nimreps is obviously basis dependent, because if some operator is realized with integer coefficients in one basis, it's not going to be realized with integer coefficients in another basis. So the deep statement of these two-dimensional systems with non-symmetries is that there exists a basis. There exists a basis. It's a special basis where the symmetries are realized by matrices with non-negative integer coefficients. This can be proven using physics arguments, and I'm happy to go over it, preferably maybe at the end, because this is it's a story of its own. But this fact constrains very much everything. So everything I'm going to say in this talk will be indirectly due to this strong constraint on the action of these symmetries on the infrared. So there is a special basis. We know how to construct it. And in this basis, you have to get nimreps. And many mathematicians are working on classifying such representations with integer coefficients. It's not an easy problem. These nimreps, they're called representations because they satisfy this algebra. So let's just go over it in this example. You can ask, can we ever represent these U's and N's by matrices that act on the Hilbert space with matrices with non-negative integer coefficients? And let's start with 1 by 1 times 1 matrices, namely ordinary non-negative integer numbers. So you can ask, can it be that the ground state is made out of one vacuum, just one state? And the answer is that obviously no, because if you say that U has to be an integer, then it has to be 1. Then N could be any integer. This doesn't place constraints. But then N times N has to be 2. And there is no integer whose square is 2. So you rule out the existence of one vacuum immediately. And that's very surprising. So you say that any system that has this funny symmetry cannot have two ground states. Cannot have one ground state. You can similarly, but a little bit more difficult, rule out two-dimensional representations. So any system that has this symmetry cannot flow to one state or two states, but you can realize it on 3 states. So it's actually possible that there will be 3 degenerate states in the infrared limit. This is a very strong claim. It might remind you a little bit about anomalies, that sometimes we can prove strong claims about the infrared. But here I didn't even use anomalies. I only used the fact that we know that this is a symmetry. Just from that, you can conclude immediately that the ground state must be at least 3-fold degenerate. At least 3-fold degenerate. 1 or 2-fold degenerate ground states are disallowed. So now let me show you how you can realize this algebra on 3 states. So let's call the 3 states V0, VA, and VF. Now here I wrote some sort of algebra between the states. That's not going to be important, but for the experts, I will say that when I write products between states on S1, what I mean is the Frobenius product, which is the pair of pens. But that's not important. It's not important for anything I'm gonna say. We have 3 states, V0, VA, and VF, and U and N can be realized with this integer valued matrices. And you can check that N times N is 1 plus U, and U commutes with N, and U squared is 1. Okay, so this is the smallest allowed integer representation, and it can act on 3 states, which we call VF, VA, V0. So that's an immediate corollary of just knowing that the system has such a funny symmetry. So, once you realize that, it's clear that if you find interesting gauge theories with such symmetries, you can make immediately strong inferences about the possible dynamics of such theories. Everything reduces to asking these kind of questions about nimreps. Are there any questions about this example?
I got a question.
Sure.
So can you explain again why it has to be integer valued representation?
Yes, I actually did not explain it. I'm happy to explain it at the end. Would you stay Would you stay until the end, like in the half an hour after the talk?
Okay.
I'm happy to give you. I can give you a full explanation, physical explanation of where this comes from. I did not explain it now. I'm just giving it to you as given, but I'll explain it at the end. To explain it properly, I have to to explain it properly, I have to maybe introduce a few more concepts from.
Okay, thanks.
So for the case of
another
the,
question.
Yeah.
I have question.
Sorry.
Yeah, for the case of the Ising model, so there are 3 gapped states.
No, in
Each
the
other
Ising model, it's gapless. In the Ising model, it's gapless.
It's gapless.
Yes, it's a CFT.
Also, so you are considering pure Ising model. It's like it's not like some deformation of it.
Right. Actually, in fact, this symmetry is violated if you deform by the spin operator, because
Right.
and it's also broken by the energy operator, because curly n does not preserve the energy operator, so it only acts at the fixed point.
So this is purely conformal field theory then.
Yes, this is the Ising case.
So what do you mean by gap? You said it's gapless.
It's gapless. I just said that this kind of symmetry can be realized on gapless states, such as the Ising model at the fixed point, but it can also be realized on gapped states. And the non-trivial claim that I made was that the smallest gap state that it can be realized on has 3 degenerate vacua, which are gapped. 3 degenerate gapped vacua.
So I see. So it's like a tricritical Ising?
No, tricritical Ising is also, yeah, tricritical Ising has a deformation, which leads to 3 gapped vacua. Yeah.
So this applies to them.
Yes, the tricritical model has a deformation which leads to 3 gapped vacua, and such a symmetry can act on them. Actually,
so these gaps need not be degenerate though. They should have same mass or can have
these 3
different
states
mass.
have to be degenerate. Yes, these 3 states have to be degenerate vacua.
Okay, thank you.
Yeah, this is actually, in the tricritical model, there is a long known fact, which is that some deformations have 3 vacua. But why 3? It's not protected by any symmetry of the tricritical Ising model. And the answer lies in this. The reason that there is this phase with 3 states is because of this symmetry, actually. This is the only explanation, actually. It's because there is this non-symmetry, and you cannot have less than 3 states if it's there. So actually, it provides an explanation for a trivial fact from statistical physics from 30 or 40 years ago.
Yeah, but in the tricritical Ising, actually, there is a quantum group symmetry, and that symmetry can explain this degeneracy, in fact.
I think that these are not unrelated.
Mm-hmm.
Any more questions?
Okay.
Yes, I have a question. So does NIMRAC also contains the information of the defect Hilbert space, or it only contains the information of the bulk Hilbert space? The
NIMREPs, this is a somewhat technical question that I'll be happy to discuss later more. But the NIMREPs, I'll answer it now. The NIMREPs contain much more information than just the defect Hilbert space. They contain the information about the defect Hilbert space, but they contain even more information. I'll explain at the end, when this talk ends, if people want to know, I'll explain that the NIMREPs contain information about the defect Hilbert space, but not just on the circle, but also on the interval. So it contains even more information than just the Hilbert space on the circle, the defect Hilbert space on the circle.
Okay, thank you.
Any more questions?
Hi, I have a question. So you showed that this NIMREP is consistent with the 3 states, but don't you have to worry about the possibility of any higher dimensional representation in the scenario?
You definitely do.
Right. So you showed that 3 is consistent, but it doesn't mean that it must be 3. Isn't that right?
You're definitely correct. It can be realized on more states too. What I meant to say was that it cannot be realized on 1 or 2 states. The minimal number is 3.
Okay, that's okay. Fine, thank you.
Yeah, you're definitely correct that there are higher representations.
Thank you.
Any more questions? Okay. So I will not go into much detail about this business of fusion categories. I want to get to gauge theories and show you some cool applications of these ideas. But I'll be using three notions, like three things that I already used. I want to summarize them, and those are the only three things that I'll be referring to. So first, there is the notion of fusion. What is fusion? Fusion is the algebra. It's just these rules. This is called fusion. This is the rules of how you fuse various symmetry or non-symmetry lines, which you can just call T. And these are some non-negative integer coefficients, which you've seen in this example already. So 1 plus u. It's some linear combinations with integer numbers. Another notion that will be very important is the action on local operators. So any quantum field theory doesn't have to be conformal. In any quantum field theory, once you take a local operator, any local operator, like sigma here, and you surround it by a defect, which could be a non-symmetry or a symmetry, doesn't matter, you get some new local operator. That's true in any quantum field theory. And so this is a very important piece of data. So you want to know how your non-symmetries act on local operators. This is super crucial because once this is already that you already asked about such things, when you want to know which deformations are consistent with the symmetries, which flows can be triggered, you want to know how the operator is transformed under these non-symmetries. And finally, there is the notion of NIM-reps, which is telling you how the symmetries, non-symmetries, act on the ground states. And the statement there is that they act with integer valued matrices, non-negative integer valued matrices that satisfy the exact same equation as this, except that here little n is an integer matrix. So these are like representations of the fusion algebra with non-negative integer matrices. That's why they're called NIM-reps. So these are the only three concepts that we will need. And now let me start by discussing gauge theory and show you some applications. So a very interesting gauge theory in 2 dimensions is the adjoint model, adjoint QCD. So the cast of characters is an SUN gauge theory. That's the usual kinetic term. And the fermion in the adjoint representation. And this fermion is real. So psi plus is real and psi minus is real. So this is the minimal adjoint gauge theory that you can have in 2 dimensions. So this is the minimal content, minimal possible content. Now this model has fermions. And when we analyze such a model, we have to specify the spin structure. But soon I will sum over the spin structure. Just for a moment, I will not. For the next slide here, I will not sum over the spin structure for the next slide or 2. But at some point, I'll just sum over all the spin structures, like I do some kind of GSO projection. And the reason is that this will simplify the presentation of the symmetries of the model. Okay, so let me just tell you a few facts about this gauge theory, which appeared in the literature before. This gauge theory was studied in many papers in the 90s and also recently. So the massless point in this gauge theory is special because at the massless point, the fermion has no mass, and therefore there is an axial symmetry. In this model, because the fermion is real, it's only a Z2. So all you can do is to flip the sign of psi plus and leave psi minus intact. That's an axial Z2 symmetry that appears only at the massless point. And you can think about it as left moving fermion number. Another symmetry that, by contrast to this one, exists for all mass is just the center symmetry. So we don't have matter particles in the fundamental representation. So there is a higher symmetry. There is a one-form symmetry, which is isomorphic to Zn. It will be important to know this fact, though I haven't explained anything about one-form symmetry, but I'll just tell you intuitively what this whole thing means. What this whole thing means is that since there are no fundamental representations here, also no representations with 2 boxes, you only have an adjoint. So that means that the number of strings is a good conserved quantum number. That's all it means. So you can discuss a vacuum without strings. You can discuss a vacuum with 1 string, 1 fundamental string, 2 fundamental strings, up to n. And at the point that you have n fundamental strings, it's indistinguishable from the usual vacuum because you have an adjoint fermion that can screen them. So all this whole thing's higher symmetry means is that we have to discuss vacua with strings and vacua without strings, and the number of strings is conserved mod n. That's all it means. So I'll often refer to the vacuum with strings, without strings, and but it's conserved modulo n. So that's why there is a Zn here. Finally, there's of course fermion number symmetry, which is part of the Lorentz group, the spin group, and that's it. So these are all the symmetries, and the massless point is especially interesting, actually. You might think that the massless point is not particularly interesting because it only has an extra Z2, but this extra Z2 is super important. So the first observation, which was made in the 90s and elaborated upon very recently in some papers that I'll refer to, was the following surprising observation. This theory has an anomaly, a 't Hooft anomaly, that involves this Z2 axial symmetry and the string conservation number symmetry, the one form Zn symmetry. So for those of you who know about such anomalies, what it means is that if you put the topological conserved charge of Z2 axial, this is like the defect. This is like the unitary Z2 axial line. Then once you take the generator of string number across, you pick up a minus sign. What it means in practical terms is that acting with the conserved axial symmetry on the Hilbert space generates n/2 strings. And n/2 is something you can only discuss for even n. So this anomaly only exists for even n, and that was understood in the literature already for a long time. So basically what this whole thing means is that the axial symmetry line creates n/2 strings. So you act with this unitary on the Hilbert space, this unitary that we talked about at the very beginning, this thing, just some Z2 unitary, you act on the Hilbert space. You create, knowingly or unknowingly, you create, because of the anomaly, you create n/2 strings, okay? And this leads to a surprising outcome. Of course, this whole thing makes sense. Well, this leads to a surprising outcome, which is that the Wilson line in the representation, which has n/2 boxes, has a perimeter law. Why is that true? Because if you can create n/2 strings with a topological operator, that means that the strings cannot be confined. If you have confined strings, then there will be some area dependence. But an area dependence is inconsistent with the topological nature of this defect. So immediately from only this anomaly, you can infer that the massless theory has deconfined quarks with n/2 indices in the fundamental representation. However, as soon as you turn on a non-zero mass, they're confined, because then this is not a topological operator anymore. It's not conserved. It's because once you add the mass, this is not a symmetry, so the corresponding operator is not conserved, and you get confinement. Are there any questions about this argument? Okay, so for SU2 gauge theory, this argument ends the whole story, because for SU2 gauge theory, n/2 is 1. So that means that the fundamental representation is deconfined in the massless theory and confined in the massive theory. So therefore, Gross et al., who studied this model in the 90s, concluded right away that SU2 gauge theory is deconfined at the massless point. That's actually a very surprising conclusion, because this is a gauge theory with no fundamental matter. How come that it's deconfined? Well, one thing that you can find consoling is that it's only at the massless point. It's deconfined only for the massless point. Once you turn on a finite mass, it's confined. But it's actually a very puzzling fact that a gauge theory like that can deconfine fundamental quarks at the massless point. But it's true, it just follows from this anomaly. Now, the more general argument that I just gave you about the deconfinement of the representation with n/2 boxes, that was done recently by this group, and it's a correct fact. So that's where you stop if you only use ordinary symmetries. So far, we've only used ordinary symmetries, and that's all we can say. But this is not satisfactory because we did not answer the question of what happens for generic N for the fundamental quark. We only answered that question for SU2. So what I'm going to do is I'll show you that this system actually has a huge amount of non-obvious symmetries, which are non-invertible, actually exponentially many in N. And then I'll show you that this can be used to prove various things about this gauge theory and compute various things that were not computable before. So let's just start as a warm-up exercise with SU2. As I said, SU2 is not really interesting. It was already addressed by these papers by Sherman et al. And Gross et al. And the anomaly fixes the answer. But just to warm up, let's discuss the symmetries of SU2 again. When we sum over the spin structures, the fermion number symmetry disappears. There is some dual symmetry that emerges instead. And in addition, the axial symmetry disappears because of some anomaly, and you get something else instead. So once you bosonize the SU2 gauge theory, you find exactly this thing that we discussed in so much detail. And we immediately know that that means that SU2 gauge theory has 3 vacua if it's gapped, which is assumed here. We just assume that this gauge theory, yeah, by the way, I should have said that. I'll assume throughout the talk that this gauge theory is gapped. It's not a big assumption, actually. It can be basically proven, but I won't go through it now. I'll just assume everywhere that it's gapped. Sorry. So if you just assume that it's gapped, you immediately conclude there are at least 3 vacua, which are exactly degenerate. Now, one of these 3 degenerate vacua has a string. It has string charge 1. So that means that a vacuum with a string is degenerate with a vacuum that doesn't have a string. That means that the string has no tension, doesn't contribute to the vacuum energy. So that's the same as the proof of deconfinement. So we just reproduced the proof of deconfinement for the mass test theory because we found that one of those 3 vacua has a string. Now, the surprise is that the SUN model actually has a huge number of hidden symmetries, 4 to the power n. That's the order of magnitude. And these symmetries constrain the dynamics very, very tightly. And I'm just going to spend like 15 minutes telling you about some of the things you can derive from these extra symmetries. For SU2, as I said, you cannot say much more, but for the general case of SUN, you can actually do some very interesting computations using this very large number of new conservation laws. Are there any questions about SU2 or the statement? Okay. Okay, so how do we classify the defect symmetries of this system? The problem reduces to a problem in representation theory or fusion algebras, which is the following. First, you take your n² - 1 adjoint fermions and you convert them to a bosonic model, which is spin n² - 1 level 1 Wezzo-Minowitten model. Now you need to gauge SUN, right? Because we're talking about an SUN gauge theory. So you need to gauge an affine subalgebra of a spin n² - 1 level 1, which is isomorphic to SUN level n. And the problem is therefore to find all the non-invertible symmetries of this thing which survive the gauging. This is a very difficult problem to do explicitly, but for small values of n, we actually did it. It's in the paper explicitly, and one can write it down in full glory. So this is how we actually found the non-invertible symmetries, but you cannot really write down the full answer for all n very clearly. You can just write it implicitly. At least we were not able to. The case of n = 2 is very easy. That's the case that we already disposed of. It's because spin 3 level 1 is isomorphic to SU2 level 2. So what you're doing is you're looking for lines of SU2 level 2 which are invariant under an SU2 level 2 subalgebra. And that problem is known. It was solved many years ago. Also, n equals 3 is somewhat easy because there is another isomorphism that you can use to reduce the problem to one that was sort of done many years ago. But starting from n equals 4, namely SG4 gauge theory, this is a much more difficult problem, and we use something that's called alpha induction to find the correct algebra of symmetries in the system. I am not going to explain that picture, but there is a dual Chern-Simons way of thinking about this alpha induction. I can explain it later. Also, I want to make a comment that this huge algebra of symmetries is only pertinent or only important, only existing for m equals 0. As soon as the quark gets a non-zero mass, what we found is that basically all the symmetries disappear. So the statement is that massless adjoint QCD has this huge symmetry algebra, but as soon as you turn on a non-zero mass, the symmetries are broken. Now, the fact that the symmetries are broken is not the end of the story, because they're only softly broken. So it's like in QCD, the fact that the pions are massive is still interesting. We can still do many things. And actually, some of the most important results I'll tell you, most concrete results I'll tell you are about the softly broken regime. Okay, so now let me get to the main claims that you can derive. I'll stop after each one of them to ask if there are any questions. First, you can ask about confinement of the fundamental representation. Remember that we could not make a statement about it using ordinary symmetries. It turns out that there is a non-invertible symmetry which creates one string, and this symmetry is topological in the massless theory. So basically what you find is something very similar to this story before. There is a symmetry that creates one string rather than n over 2 strings, and it's topological. So once you find that, you're done. So this is a one-line proof after you find this particular non-invertible symmetry. It's a one-line proof that all quarks are deconfined. So in this model, all the quarks in all the representations are all deconfined at the massless point. Not just the representation n over 2. And this is true for all n. Next, we can ask about the vacua. I told you that once you have these funny algebras of symmetries, typically there are many vacua. It would be inconsistent to have one vacuum or two vacua. Actually, what we find here is that for generic n, the smallest allowed nimrep seems to be huge, 2 to the n. So we claim that there are 2 to the n of order 2 to the n degenerate ground states. This is very unfamiliar. If you think about 4-dimensional gauge theories, 3-dimensional gauge theories, like super Yang-Mills, they usually have n vacua or one vacuum. This model is bizarre in that it has, when it's at the massless point, it has an exponentially large degeneracy of the ground states. This is bizarre. And we also made a proposal for a topological field theory that describes this huge degeneracy. This is a particular topological theory. It has zero central charge, which could describe. We actually proved that this is the answer for small values of n, but not in general. The fact that there is a huge number of ground states is guaranteed. Finally, you can ask about the strings. So the strings at the massless point are not terribly interesting because they're tensionless. Because of the confinement, the strings that the quarks create don't have any tension. As soon as you turn on a non-zero mass, it's a very interesting question to ask about the string tension. Now, when the mass of the quark is huge, the adjoint quark, this problem is very easy, and it was solved by Migdal in the 70s, because when the quark is very heavy, you can integrate it out. The problem reduces to some problem in pure Yang-Mills, and there is this famous Casimir scaling that Migdal found, and many lattice people have been pursuing since, and you find the following tensions for K strings. So this is what you find at large mass for any n. You find that the K string tension obeys this Casimir scaling. For small mass, the problem of finding the string tension is very difficult because this is a strongly coupled regime. As I said, now the mass has to be non-zero, for otherwise strings are exactly tensionless. So this is actually a problem that one can solve using topological field theory techniques. involving these NIMREPs and the huge symmetry algebra that we found. So what we did was, what this problem reduces to is to understanding the action of the symmetry, non-symmetry lines on the local operator, which is the fermion condensate. Remember that I told you before that one important thing is to understand how these non-symmetry lines act on local operators. This is what you need to do to understand the string tensions at small non-zero mass. So we basically had to solve this problem of finding how this huge symmetry algebra acts on the fermion bilinear local operator. This can be done. It's very tough, but it's very technical, but it can be done. And that's what you find. You find that the K-string tension obeys this beautiful sign formula for all K and N. That's what we found. Or more explicitly, this is the tension of the K-string. So it has a finite scaling with N. It's proportional to the mass because the tension has to go to 0 when the mass goes to 0, and it has this sign. More precisely, our computation is just in the limit of very small mass. We're using softly broken non-symmetries. So our computation is only for like very small mass. So there could be some corrections, which we don't know how to compute at the moment using these techniques of softly broken softly broken non-symmetries. There is a small puzzle here that I wanted to mention quickly, which is that the Casimir answer of Migdal and our results suggest a different scaling in N for the binding energy of two strings. So in the small mass regime, what we found is that the binding energy of two strings goes like 1/n². While at large mass, that's what Migdal found. And there is a slight mismatch. It would be nice to know how this is resolved as a function of the mass. Finally, before I stop for questions, I'll just mention that such a sign formula appeared before for some BPS computations that were done by Herzog and Klebanov in a completely different system in holography. I don't know why there is this similarity. An additional computation that led to a similar formula was done by Armoni, Dorigoni, and Veneziano, which used Samaguchi-Kawai reduction and got a similar formula for, again, unknown reasons to me. It's completely different techniques. It's a different theory. It's a different setup, but it's the same formula. Okay, I would like to stop here before I make some comments about naturalness. Are there any questions about any of these applications? Right, let me just continue. So one final thing that I wanted to mention is the fact that this gauge theory can also be deformed by quartic operators, such as this or that. And these are the only quartic operators that I will discuss. They are the only ones that preserve the chiral symmetry at the massless point and do not break charge conjugation symmetry. So these are the only ones. They are trivial for SU2, but they're non-trivial for SU4 and higher. Okay, so you can ask, what happens to the symmetries, the non-symmetries, when you add this to the action? So O1 is actually very amusing. O1 doesn't break any of these huge symmetries that I discussed. So all the 4 to the n symmetries remain. And therefore, everything I said remains correct. O1 doesn't change anything in what I said. O2, on the other hand, is more difficult. O2 breaks some of the non-invertible symmetries, but not all of them, some of them. And you can add it to the action, and you can use the techniques of softly broken defect symmetries to understand the dynamics. What you find is that with one sign, it leads to the scenario that I mentioned before, which is a deconfined quark with a nullity n/2, but all the other quarks are confined. So that's what happens when you add this operator with one concrete sign. If you add it with the other sign, we got some funny phases that we don't understand with some negative string tension, and we don't know if adding this operator with the other sign is actually allowed. And here I just wanted to finish with a philosophical comment about naturalness. If you are doing Wilsonian field theory, this operator is allowed because it's invariant under charge conjugation symmetry, it's invariant under the axial symmetry, it's Lorentz scalar, but actually it's never generated. And this is a funny violation of the usual notion of naturalness, that we have an operator that seems okay, but it's never generated. And you can actually do a computation of the beta function, and you would see that it miraculously vanishes. It just never generated. This would seem very puzzling, but now, of course, you see the answer. The answer is that this operator breaks some non-invertible symmetries. So we see that the criterion of naturalness applies to non-invertible symmetries too. And actually, if you are to add this operator with a small coefficient, it would only be renormalized multiplicatively. So that's very much like fermion masses in the standard model. And of course, one can speculate that maybe something like that is interesting also in higher dimensions. Of course, the whole problem of the Higgs mass fine-tuning and naturalness is about why is it not generated with a large coefficient. Here we see an example of an operator that is actually dangerous. It changes the dynamics quite substantially, but it's not generated because of some hidden non-invertible symmetries. And that's the end of the talk. So thank you. Thank you.
So I guess we could ask whether there is any questions from audience.
Can I ask a question?
Yeah, sure.
Sure. About your last comment about this naturalness of the double trace operator, is this still true in higher dimensions, or is it special to 2 dimensions?
Well, that's an open question. I am not familiar with interesting systems in higher dimensions that have such non-invertible symmetries. This phenomenon that I talked about of the existence of this huge algebra of non-invertible symmetries, I don't know of an interesting, example of that thing in higher dimension.
Okay, thank you.
So maybe, yeah, it's just a 2-dimensional example of something amusing, which could be nice if it were true, if it was possible in higher dimensions, but we don't know yet if this is possible.
So any other questions?
Do you have any intuitive explanation why this this weird non-symmetry exists in 2 dimension, but not so much example in higher dimension?
It's a great question. I wish I knew the answer.
Oh, okay.
Yeah, it's really a good question. I can mumble some things, but they're not terribly convincing. So I don't know what exactly to say, unfortunately.
Or even technically, can you just comment on that? Why?
I can make a small technical comment.
Mm-hmm.
So you can realize this adjoint QCD model
Mm-hmm.
as a quantum Hall state. So you can think about a 2-dimensional system on an interval, finite interval. And then when you go to low energies, it becomes 2-dimensional because the interval size disappears, yeah?
Yes.
But how do you realize it on an interval? You need several ingredients to realize this adjoint gauge theory. One is in the bulk of the interval, like in this white space, you need to put some non-abelian Chern-Simons theory. Concretely, you need to put SUN level n. Second ingredient that you need is that you need that on the edges of the interval, which are these black thick lines, you need kinetic terms, which are purely 2-dimensional for SUN. So SUN is topological in the bulk, but dynamical on the boundary. And the final most important ingredient, actually, that without which this doesn't work. Okay, so if you didn't have this funny red line, what I call the surface operator, this thing that I just described would flow to a topological field theory of the type SUN level n, quotient SUN level n. It has nothing to do with a joint QCD. To make contact with a joint QCD, you need to put a surface operator, a certain surface operator, and then it's really the same. And these non-invertible lines can be described in this 3-dimensional. This non-invertible, sorry, there was a comment?
No, go ahead, please, sorry.
These non-invertible symmetries in 2 dimensions can have like an origin in the 3-dimensional picture as the Wilson lines in Chern-Simons theory. And these Wilson lines have funny crossing rules with the surface operator and so on that you have to understand. but they really originate from Wilson lines in 3D. Now, somehow, you know, like three-dimensional topological filters are the most interesting. So maybe that's why these non-invertible symmetries in 2D are somewhat common. But there are non-trivial topological filters also in 4D. Like there are Digraph-Witten theories. And I don't completely understand why there are no similar constructions in 4D yet. I don't see it yet.
I see.
It could be that it's the surface operators that are lacking. I don't really know what's going on, of why this is not so easy in 3D.
Thank you very much.
All right, any other questions?
I actually have a question. So, are these non-symmetries necessarily discrete?
I've never seen a continuous example. I'll make a few. One, I've never seen a continuous example. Two, in all the examples that I've seen, you can understand them through some three-dimensional construction that involves a quantum Hall state with some surface operators. And in all those examples, they will definitely come out to be discrete. And finally, I'll say that the mathematical literature on fusion categories always assumes that there is a finite number of simple lines. So this discreteness seems to be more or less imposed in the mathematical literature and also present in all the examples I know in physics.
Okay, thank you.
So, any other questions? So can you have higher form non-symmetries?
That's an excellent question. I mean, can it be that there are non-invertible higher form symmetries? That's an excellent question. I have no idea what's the answer. I mean, probably the answer is yes. When I said that I have no idea, what I meant is that I don't know if there are interesting, interesting cases with interesting examples, something that, you can do. So I don't know if there is an interesting thing out there.
I think there was one more question somewhere.
Could you say a bit more on the NIMRAP?
Yes. Maybe I can spend 5 minutes on it now to explain where the NIMRAP comes from. Is that okay? Kim Young?
Sure. Yeah.
That's a very cute piece of this whole story. Okay, so let me start with some two comments, general comments. One is that when you take this infrared limit and you look at the states on the circle, you just have a Hilbert space of n states. Who asked the question, by the way, so that I know more or less who am I talking to? Would be more convenient.
Oh, it's me. Qiming.
Okay. So when you have n states on the circle, and at that point, all the usual rules of quantum mechanics apply, and you can perform arbitrary basis changes of these n states. You can perform arbitrary complex valued linear transformations. So once you have n degenerate states on the circle, you can do whatever you want. It's just the ground state space of the theory. Now, a very interesting and important question that we have to address before we go to NIMREPs is how are these states related to superselection sectors? Because by the time we go to infinite space, we have this picture of vacua, like some potential with some vacua. And these vacua are like some particular linear combinations of the states on the circle. But when we get to infinite space, we don't have the ability to perform arbitrary linear transformations anymore. Like if you look at the books on QFT, nobody does linear combinations of superselection sectors. It doesn't make sense. So first, there is a question of how do you find out the canonical basis of the states on the circle, which ends up being the correct states at infinite volume. Okay, so there is a very special basis. And that breaks, okay, so you have to find this basis. Now, let me just use the chat to write this basis. So to write down this basis, I have to introduce one little component, which is that in any basis, if you multiply Vi and Vj, you get there is a notion of multiplication. Okay, so in ordinary quantum mechanics, we have states, we have linear combinations, but it doesn't make sense to multiply states. But in this setup, where we have a quantum field theory that flows to some n states on the circle, there is a notion of multiplication of states, which is in any basis, which is given by some matrix, which is called the mu matrix. So you have a matrix with 3 indices, and you can multiply states, mu I, j, k, and you can multiply states. And that's true in any basis. Why is the notion of state multiplication sensible? It's sensible because you can use the state operator correspondence. It's true in conformal field theories, but it's definitely also true in gapped systems. And in gapped systems, every state on S1 becomes a local operator in a flat space. And local operators have an operator product expansion structure. So there is a canonical way to introduce a product structure on the space of states. So what the statement, which is non-trivial, is that the correct basis, which in the end becomes the basis of superselection sectors, is one where mu is completely diagonal. So mu I, j, k is delta of I, j times delta of I, k. All the indices have to be the same, and there is some constant ci in front. So there is a special basis like this, where all the mu's are completely diagonal. So v times v is the same as it. And actually, I briefly mentioned here, you see? So this was in the diagonal, in this special basis. So everything times itself is up to a constant, the same as what you multiply, up to some constant, which is called ci. Okay? So such a basis exists. It's a mathematical theorem. And that's the basis that becomes the superselection sectors in infinite volume. Okay. Now, it is in this basis that these symmetries are realized by integer valued, non-negative integer valued matrices. Why is that? So this is the basis of good states on R. So this is the basis of good state of boundary conditions in some sense, because states on R are obtained either from infinite volume limit of S1 or from an interval with some fixed boundary conditions that you take to infinity. So if you assume topological symmetry, acting on these special states VI is the same as looking at the defect Hilbert space with some boundary conditions. You can just use like a 90 degrees rotation. So imagine an annulus. Imagine an annulus where you put some special states VI in the future and the past. And these VIs are the good states, like the good bases that become good superselection sectors. Now put an operator like U or curly N or any such non-symmetry, put it like on the wrapping the cycle of the cylinder, of the annulus. And now rotate this picture by 90 degrees. You can now take the infinite volume limit because of topological invariance. And since these are good boundary states, you get the defect Hilbert space. And therefore, you're just counting the dimension of some defect Hilbert space on an interval. And that's got to be an integer. So a very important point here is that you must find this basis of good boundary states. Only there it is true that you're counting the dimension of something. So that's how you arrive to this notion of NIM-reps. And that's why mathematicians who work in this field are basically looking for, that's what they do. They look for solutions of these equations in integer valued matrices.
So this small ni is what? Coefficient of the scale of the state? Small ni, right at the bottom of the, yeah.
This is the matrix which represents the non-invertible operator on the Hilbert space. So it's a matrix with which it acts.
Oh, matrix, okay.
Yeah.
What's the index I and j then? Oh, those are the like
the collection of matrices. Every operator Ti, non-invertible operator Ti, becomes a matrix Ni on the Hilbert space. And this is just the algebra that these matrices obey.
All right.
Yep.
Right. So, any questions or any request for Zohar to expand this explanation?
So does
I
the
have
NIMRA also tell you how many operators, for example, how many operators in the defect Hilbert space? Does that also tell you the spectrum of defect Hilbert space? And how fusion works in defect Hilbert space?
You're talking. Are you asking about the defect Hilbert space on S1?
No. So I'm asking about so there could be operators that at the endpoints of of these defect lines.
Yes.
And does this NIMRA also contains the information, for example, the OPE of this operator, something like that?
No, it only contains information about the degeneracies.
Oh,
It does not contain information about the algebra. No, it does not. It only contains information about the number of topological endpoints.
I see.
Well, in fact, as you know, we typically assume that non-trivial lines cannot end with non-trivial topological local operators. So we typically assume that home 1, A for non-trivial simple lines A is vanishing.
Okay, yeah.
Typically we assume that, but that doesn't mean that these NIMREPs are trivial, because once you have non-trivial boundaries and you're starting an interval rather than S1, then this is like asking something about the junction. And at the junction, there could be a non-trivial degeneracy of topological local operators. So basically, this is what these matrices measure. These matrices measure the number of topological local operators in some junctions.
I see. Okay, thanks.
I think there's also one more question from the audience.
Yeah, I have one question. So in this gauge theory, you are saying that it develops a mass gap even this parameter m is 0?
Yes.
How do you know that?
Well, if you let me just make some claim, some statement you didn't ask about. Even if you assume that it develops a mass gap, well, I assume that it develops a mass gap in this presentation, okay? And once you make this assumption, you can prove the confinement. Second, you can prove that there are exponentially many vacua, which are degenerate and gapped. And thirdly, I talked about the quartic deformations. Now you're asking a more basic question, which is how do we even know that it's gapped?
Right.
Okay, this is a very interesting question. And you cannot really prove it, but you can make some claims for why it's sensible. So let me give you a claim why it's sensible, and then I'll tell you about some other evidence. So the first claim of why this is a sensible thing to do is that if you first bosonize the fermions before gauging the SUN, you get this WZW model. And then you need to quotient it by the gauge symmetry, which is this. And actually this quotient, I wrote it somewhere here, this quotient has vanishing central charge. So if you compute the central charge of this Wieso-Minowitten model and subtract the one of this, you'll find 0 exactly. So what this means is that the infrared doesn't have any reason to have massless. There is no CFT in the infrared. But you could still have many discrete degenerate vacua. That's one argument. Another argument is from a lot of very beautiful work that was done numerically by Klebanov, Gross, Hashimoto, and others. Let me just find the names. This group did, some of these people in the group did many DLCQ, the DLCQ studies of this model, and they found very strong evidence that it's gapped.
that they consider same model or some related model?
No, exactly the same model.
Mhm.
They basically simulate with DLCQ the massive model with m not equal to 0, and they can go to very low mass, and they see that the gap remains.
Did they find also the degeneracy, correct degeneracy?
No, all these things that I said are new results, including the string tensions. You can ask, can they verify this since they simulated it numerically, just to compute the tension of strings? And the answer is no. And the reason is that when you do DLCQ, nobody knows how to put strings. So DLCQ tells you about the spectrum of the vacuum without strings. So this statement, all the statements that I made about the existence of exponentially many vacua, zero temperature Hagedorn transition at large n because of this exponential growth, the tensions of the strings, none of this can at present be checked with DLCQ. But they found a lot of evidence that the model is gapped, and yeah, that's basically the reason that I believe that it's gapped. I'm completely convinced that it's gapped.
Okay, thank you.
Okay, so is there any other questions or requests?
There is something in the chat. Let me just check. In a gapped system with non-invertible symmetry, are the ground states all exactly degenerate or degenerate modulo exponentially small energy? That's a very interesting question. The answer is that we have, in this system, we have 2 to the n vacua. They're all related to each other by non-invertible symmetries. Most of them are not exactly degenerate. There are small splittings which are exponentially small. There are exponentially small splittings in the volume of S1, except that n of them, there are exactly n out of this 2 to the n that are exactly degenerate even in finite S1. So the reason being, I wrote it somewhere before, the typical splittings that you get on S1 are exponentially small, and there is some scale in that exponential, which is this t. That's like the mass of a kink. So some kinks actually have infinite mass. Very few of them. Most of the kinks are finite mass. But some kinks have turned out to have infinite mass, and so a few of those states are actually exactly degenerate, even on S1. But most of them are split by exponentially small terms. That does not mean that the statement about NIMREPs is not correct. When to arrive at this whole idea of NIMREPs, you need to take this infrared limit, drop these exponentials, and then do this 90-degree rotation. Any other question? These are very good questions, but yeah, so thank you. There is one more comment in the chat. Okay.
So any more? Well, so what's the, say, future direction in this non-symmetry?
Well, one thing that I'm trying to, well, even n equals 1, the supersymmetric version of adjoint QCD, like n equals 1, I don't really know what it does. No, I don't think anybody knows. So I'm trying to think about it using these tools. Secondly, there is a small paradox here of how the string binding energy makes sense. We arrived at this paradox that matching the small mass limit and the large mass limit is not the same. So I'm trying to understand that. Thirdly, there is a question of how to classify these surface operators and what do they, like how to think about them in more generality. So we're thinking about that. That's actually possibly related to this paper by Dongming Gang, and collaborators from recently. Then there is a question of like the existence of K-strings. Actually, the fact that the binding energy of these strings here is positive, that there are bound K-strings, is not obvious. And many models that people looked at before don't have bound K-strings. And there is a question of what happens if you look at an adjoint model, like an F adjoint model. You have more adjoints. Do you still have bound K-strings or not? That's another question, and so on. I mean, there is a long list of various things that are open. And I mean, basically, if once you open the floodgates for saying that, you know, there are many symmetries that you didn't know about and they have lots of consequences, I assume there will be many applications.
Excuse me?
Yeah.
Is there any reason why you say the binding energy mismatch is a puzzle? Because, you know, is there a different mass regime? So is there a particular reason why you feel it?
Yeah, I think the thing that, well, I'll tell you why I don't understand. I mean, it's a discussion, so I'll tell you what I don't understand. First of all, if you just think about a holographic model, like, you know, this is in large N. I did a large N expansion here. So if you think about a holographic model, the fact that there is no 1/n at small mass is very strange, because there is a diagram that you can draw, which should have led to 1/n. I don't understand why that diagram cancels out. This is something that I should be able to explain using these non-invertible symmetries, but like to give an a priori explanation, not a computational, like an a priori explanation of why this diagram cancels out.
So you mean the weak mass? You mean the small mass region has some surprising cancellations?
Yeah, definitely. I don't understand it actually. And secondly, I'm worried. I'm worried that you know, if there is in the next order in the mass, there is a 1/n. That means that the small mass and the large n limit don't commute completely, because if there is a 1/n in the next order, when I take large n, I cannot say anything. This result is exact in the small mass regime, but if you take large n, you might get into some confusion. And I don't understand it. I also believe that if you take more than one adjoint, there won't be any K-strings starting from an f equals 2. And I wonder if this conjecture is correct. I think that n f equals 1 is probably the only case that there are K-strings. Yeah, I don't know. There should be some transition from this regime to this regime. I don't know if this transition is some smooth transition or it's something more interesting.
Thank you.
So any more? All right. So this has been really excellent talk, Zohar, and I think everybody enjoyed it, even though it's a bit early for physicists in Korea.
And a bit late. Yeah, it's not late for me. Yeah.
All right. So if there is no more questions, then we could thank you and hope to see you.
If anybody has any more comment, you can just shoot an email. I'll be happy to think about whatever you guys come up with. And thanks so much for the hospitality.
All right. Thank you very much. Then.
Thank you.
Bye.